All right, so let's start this meeting. Welcome to this third ISSMGE TC222 online workshop. My name is Mickaël Beaufils. I'm the vice chair of this group, and I'm very happy to be here with you to do this third workshop. So you have here the agenda. We will try to fit the times that are proposed. And as you can see, for the Q&A, there is an invitation to use an app called Slido. So I would suggest you to try to reach it, and it will be used in order to ask some questions to the different presenters. And as you can see on the agenda, we have time for that. So now I will go into a brief introduction of ISSMGE TC222. And we will also introduce this topic of geotech standards that is the topic of today. So let's go for it. So unfortunately, Master Morin, the chair of this group, is not here, so I will perform this presentation on behalf of him. So ISSMGE, if you don't know it for now, is the International Society for Soil Mechanics and Geotechnical Engineering. We have 90 member societies, national bodies, and around 20,000 individual members in it. So the ISSMGE is organized in 37 technical committees. You have 7 about fundamentals. They have the name TC1 and other numbers after that. 21 about application, and 9 about impact on society. So the TC222 is about BIM and digital twins for geotechnics, and is one of the last TC that was done in ISSMGE. So the TC222 is organized with a council. So you can see who has the members of that council. So Magnus Sommer is the chair of it. I'm the vice chair. Mats Karlström, that is here with us, is the secretary. And also Jelena Linic and Raymond Koo are co-members of TC222. So together we discuss how we organize the activity and the animation of that group. Especially, we have different background and also specialty, and in order to highlight things about new technologies, about academics, about application in smart cities. If you want to follow us, there are multiple ways to do that. We have a website that is hosted by ISSMGE, and you can reach with that link. Also on LinkedIn, we have a page. Certainly some of us may have found it, and that's where we communicate about our events. And we also have a YouTube channel, and I will let you know about this YouTube channel because that's where we provide the previous workshop recordings. So this workshop is recorded, and the recording will be available a few times before this. So now we will go into an introduction about digital standards for geotech. I will explain you a little bit what it is about, and I remember you that you can have the possibility to ask some questions thanks to Slido, and with the link also that is pasted on the chat. So let's go for this brief introduction about what is digital standards for geotech. As I mentioned before, TC222 is one of the most digital-oriented TC from ISSMGE. And when you look at the topic, that is BIM and digital twins, and this target, you can see that standards are necessary to achieve that goal. So in our terms of reference, we define an objective that is writing guidelines and recommendations. And in this objective, we have something about standardization. So the plan for us is to be a link for the different organizations that are talking about standards for geotechnics. And what we try to do is to facilitate collaboration and development of standards, especially with 4 organizations, but it's not restricted to those 4. The Building Smart International, Open Geospatial Consortium, OGC, AGS, and DIGS. So you will have some presentation about those 4 organizations. And what we try to do is, well, when you are geotechnical engineers, you want to do something regarding the provision of geotechnical data. What we will try to do is to propose some guidelines and technical recommendations, so you will easily find how to do that. So if you want to know more about our terms of reference, you can have a look to it thanks to the website of TC222. Regarding the topic of digital standards, I wanted to point out one paper that is not, I would say, the position of ISSMGE. It's a paper that was written by David Toll in 2009 about the International Data Standards for Geotechnical Engineering. So this paper was proposed for the International Conference of Soil Mechanics and Geotechnical Engineering, so ISSMGE. And if you have a look to it, there are some statements that are still true, and of course, things that have changed since 2009. So what I appreciate in that paper is that there are some ideas that the topic of standardization is something that should be addressed together. So there was this idea of having a joint TC between ISSMGE, IAEG, ISRMs. This joint TC still exists. It's called JTC2. And as you can see, there is this idea that, well, standardization should be done together. And in this paper, you can see that some key players, I would say, or communities were already identified as providers of solution in order to provide geotechnical data. So these key players in 2009 were AGS, DIGS, and GeoScience. Since then, there is also Building Smart International that came. So that's exactly the 4 communities we will address today. The key challenge for standardizations, of course, when we talk about doing some standards, you can see that when you want to exchange the data, there is a big topic about semantics and semantics elements. This is due to the fact that we have different cultures, we come from different domains with different backgrounds and have different practice. So there are multiple ways to describe the same things using the same words or not. So semantics element is quite important in order to be able to exchange properly the data. And that's something that standardization should address. Another point about standardization is that you have different possible level of sophistication. So when you would like to propose a standards, you of course would like to have something human readable, but if you have an idea to reuse the data thanks to machine, this format should be machine readable, and sometimes a compromise should be found between the 2 of them. Also, when you are doing some standards, there are multiple ways to address it. You will be able to standardize everything, so you will have small boxes. This has some advantages, but also some drawbacks. And you can have another option that is having bigger containers, so things that are standardized as a whole, but having capacity to be more flexible inside. So these are things that should be balanced. And the other things is, of course, that you have a dependence of technologies. We use digital things, and so technology is running, and you have different solutions that can be offered, CSV, XML, and JSON, and of course, they have some advantages and drawbacks. So depending on the choice you make, you will emphasize different capacities and results. And I think that the standards we will have an highlight today are well showing these differences, but also similarities. I would like also to introduce you an interesting activity that was the geotech interoperability experiment that well reflect this idea to work together and to define standards together. So in January 2019, there was a geotechnical data standardization workshop that was held in Paris. And this idea was when Building Smart International wanted to address the topic of geotechnics, to try to federate with existing standards and people that were already working on that topic. So there were people from OGC, but also AGS and things that were represented. And the idea from that workshop was to try to work together to have the definition of common semantics, common tools and APIs, and also provide some guidance for people that want to expose data. So the dream came true in February 2022, thanks to the fundings of a project called Mine in France. And this idea and this project was a geotech experiment that tried to address what I just mentioned before. So this project just came to an end in 2023, December 2023. So the result of it are already available. The work plan we had in this Geotech IE was to address two things. As I mentioned before, this is to find the balance between community-oriented goal and also technical-oriented goals. So regarding the community-oriented goals, you can see that it's about working on the semantics, having a common conceptual model, provide some guidance thanks to a technical paper and also an implementation guide for software vendors. And on the other end, there was this idea that, of course, defining standards is nice, but we also want them to be implemented. And so this idea was to extend the existing OGC GeoScience standards and also provide technical documentation about how to use them with OGC APIs. So the results of this Geotech IE are available. They are mostly divided into two documents. There is this white paper that is provide you a very simple overview of what we try to do, of philosophy. And also there is a bigger technical paper that has the form of a wiki that is available from that link, and that is a kind of index of all the deliverables we provide in that project. So I will just show you an overview of what is available for you. There is first this activity that has been performed, trying to identify the geotech concepts and mapping between the existing standards. So we came into this classification. This is something that was commonly done with the IFC tunnel project, and that led to this proposal to structure our different data into book A, book B, and book C. Something that comes from the French International Tunneling Association first. So here you can see the different concepts we identify, and of course the idea was to see how they are currently addressed in the different formats, in the different standards that were part of that project. Another activity mostly focused on OGC was about the providing extension to OGC and ISO standards, while there were some developments in AGS, in DIGS, in IFC tunnel. There were also OGC activities about having these standards extended to be compliant with the proposal we defined before. And one other activity we had was to work also together on the use of API, especially one OGC API, in order to provide the geotech investigation. So we had a common activity that was to take real data from borehole logs, CPT, SPT, pressure meter, and to see how they can fit to that API. So there was the development of an API, or more exactly, extension of existing API in order to do that. And we try with people from HGS this to see how it can fit, how they can be used in order to facilitate the provision of geotech data. So that's it for my introduction of this topic of digital standards for geotech. Now I will give the hand to Neil in order to perform a presentation about AGS. And I remember you that if you have some question, either for me, either for Neil, Dan, Jonas, please use the Slido link in order to ask them, and we will have time in order to address them. So thank you. And Neil, the floor is yours.
Okay, I will just bring my slides up. Hello, can you hear me? Because I did freeze then.
We do.
You can, good. Right, I froze for a little while. It looks like you do have my slides now. That was a little bit scary. Okay,
They are
good,
full
let's go.
screen now.
That was a little bit scary. All right, good afternoon, everyone, or indeed good morning, or even good evening, depending on where you are. So my name is Neil Chadwick. I work as an independent consultant these days, although I have spent many years with a major design consultant. I'm also a member of the AGS Data Management Working Group, which I will be introducing in a few minutes' time. So I'm going to talk about the AGS data transfer format, and this is a fairly quick 20-minute introduction. And in terms of what I'm going to cover, I'm going to talk about what is it, what's its history. I'm going to have a look at how it actually works. So we're actually going to have a look at it. And we're going to look at some things that are complementary, AGSI, AGS piling. I'll introduce those, say a little bit about where AGS data might go in the future. And today is very much about interoperability, so I will do a little piece on that at the end. First of all, what is the AGS data format? Some of you will know it well, some perhaps have heard of it, some perhaps don't know it at all, but I'll start at the beginning. It is a data transfer format for ground investigation data. So that's geotechnical and geoenvironmental data. So it's used for the transfer of data between different organizations, although these days also gets used quite a lot even within organizations, perhaps between different teams. And its scope is factual ground investigation data. So this is the stuff you'll see in what we call factual ground investigation reports, Bouquet in France. So it's the stuff you see on borehole logs, but also all the test data, including the lab test data, also monitoring. And in fact, that goes beyond investigations, and AGS can actually handle some types of construction monitoring as well, although it's not quite so commonly used for that. One thing it doesn't include is interpreted or design data, but we do now have a new format that does do that, and it's called AGSI, and I will return briefly to that later on in this talk. But first of all, on the main AGS data formats, I'm going to just talk about a little bit of history and basically give a little bit of background and context. And first of all, the AGS format was first published in, believe it or not, 1992. Now, to put that into context, it's actually about the same age as the World Wide Web. I can vouch for the fact that we were using floppy disks to transfer data around at that time. Email hadn't really arrived yet. And interestingly, there weren't really any comparable standards to influence it at the time. So it kind of, I guess, it evolved in a little bit of a bubble. But we like to say that it was created by the industry for the industry. And it's over 30 years old now, but it's still using it. It's had a few updates, but it's still essentially the same. But if we're still using it, and obviously we must have got something right and are doing something right. In fact, it's been very successful. It's now routinely used here in the United Kingdom. It's on most projects, it's a standard requirement and it doesn't even get questioned. And it's pretty well implemented by the specialist software that we tend to use. But it has also been adopted and in some cases adapted in a few other countries, in particular Australia. New Zealand, I think, is relatively recent. Hong Kong, long-time users, also Singapore. Seen it take off a little bit in Ireland. There's been occasional sightings in mainland Europe and the Middle East. Now, I just want to talk a little bit about the AGS part of AGS data, because if you're not from the UK, then you probably won't be familiar with that. Well, the AGS is an organisation. It's the Association of Geotechnical and Geoenvironmental Specialists. And it's a trade association, so basically a grouping of like-minded companies. It's a not-for-profit entity. It is based in the United Kingdom and it is for UK-based companies. Its membership, we have a lot of ground investigation contractors, but also consultants, both specialist and generalist, and a few others, as you can see there. The current membership is 183 different entities, so it's a pretty strong body. Now, AGS data is actually only a small part of what the AGS does, and it's actually divided up into several working groups. But the important one for today is the Data Management Working Group, who look after the AGS format, and that's the group that, as I said, I was part of. So how does AGS actually get used? Well, I guess the most common use case is sorry, a few technical difficulties here. There we go, that's better. Right, so the most common use case is provision of data associated with a ground investigation report produced by a ground investigation contractor, data provided in AGS format to a design consultant who will then go and do their interpretation and design. And interestingly, in the UK, these are usually different companies, different organisations. That's how we tend to work, which probably explains why AGS developed in the UK and maybe not in other countries so much or equivalents. But this is only one application of AGS, because if you actually look at how the activities that we undertake before we even get to that final report, we actually find that AGS data can and often is used as part of that, as part in the supply chain, as you can see here. And then the design consultant shouldn't be the last person to see the data, because there may be other designers that are interested. There may be piling contractors, for example, who might want to see it. Good clients will be taking an interest. And we also have our British Geological Survey as well, who have always collected data, but now they're actually collecting AGS data as well. And they are making it available to us to inform new projects. So that's just a brief introduction to what AGS is about and where it came from. Now let's have a little bit of a look at how it actually works in practice. And essentially, the AGS data format is made up of two components. And the first of those is a data structure, which we define in what we call the data dictionary. You might think of that as the schema. And then we have the file transfer format. So this is how we get from the structured data to that final file deliverable. You might want to think of that as encoding. And these are defined and underpinned by a set of rules, and all this is, of course, captured in the documentation. So let's have a look at the data structure first, and say we must conform to a specified structure. And the first important concept is we divide up the data into what we call groups. And these are groups are arranged by subject area. So for example, we have exploratory hole locations and also some general metadata for the holes, basically where we define the holes, is in a group called locker. Samples of sampling are together and they're in a group called SAMP. The different in situ tests, well, we have a different group for each test type, or sometimes two. And the same applies with the lab tests as well. So that actually means that we end up with a lot of groups, and you'll see that in just a moment. And then each group gets divided up into fields, alternatively known as headings, or effectively the same thing. So for example, in the SAMP group, we have headings for the hole ID, depth, type, reference, and so on. Now this might seem like a fairly familiar concept, and indeed it should be. It's not an object model as such, but it can be mapped to that sort of structure. And indeed, it can be mapped to a database type structure. In fact, it's got a lot in common with database structures. So basically, our groups are effectively analogous to objects in an object model or the tables that you'd find in a database. And the fields and headings, that would be your object attributes or the columns and fields that you'll find in a database table. So a fairly familiar concept, and another familiar concept is linking of the groups as you would link in a database or in an object model. We've actually got a pretty logical hierarchical structure. We stick to parent-child relationships. We keep it simple. We don't have relationships dashing off in all sorts of different directions. It's implemented using the concept of shared key fields. I'm not going to go through this in detail, but you can see that basically we do have a logical flow through. Everything starts at the top with the holes in locker. And with the lab tests, we have to go through the sample first, and lab tests are done on samples and so on. Apologies for the phone if you can hear that. So here is the full schema or the full structure. So as you can see here, it's big. There are no less than 148 different groups here. Each line is a group here. So obviously I'm not going to go through all of that. Now the colors here are simply the unofficial groupings of the groups, and it's just really to help navigation. So I'm just going to concentrate on those to give you a flavor of what's actually included. And on the left hand side here, we've got locations and basically the exploratory hole construction details. We've got a set of groups that cover that. We've got a few groups that cover the geological descriptions, and then we've got samples. So this is basically information you would find on a borehole log. And then we also have, of course, geotechnical in situ testing. I've got about 20 odd groups that cover that. And then probably getting on for half the schema is actually the lab testing, as you can see here, predominantly geotechnical. We've got some aggregate stuff as well. Although interestingly, we have a slightly different structure to deal with the environmental testing because it's all held within one single group. And a similar concept is actually used for the monitoring, which is actually dealt with in a single pair of groups for different types of monitoring. In terms of the file format, so this is a snippet of a very, very simple AGS file, but it is essentially a text file. So you can open it in a text editor. We just happen to use .ags file extension for it. It is a bespoke format. It looks a lot like CSV. In fact, we call it CSV-like. It's essentially blocks of CSV data, although they do also have multiple header lines, as you can see if you look carefully. And each block here is the data for a particular group. In terms of the pros and cons of this, one of the good things is it is something that's easy to understand. You don't need to be a data specialist to be able to follow this. And in fact, pretty much anyone could, if they wanted to, paste this out, paste parts of it out to an Excel file. Not something we necessarily recommend, by the way, because there's plenty of things that can go wrong, but it does happen. File size actually turns out to be relatively compact compared to some alternatives. But the downside is it is bespoke, so it does need a bit of work programmatically to parse out if you're bringing it into an application. The documentation, it's not a British standard, and it's not an ISO standard, and that is actually a deliberate decision that was made a few years ago. It's just a document that is published on the AGS website, although it has effectively become the standard for ground data transfer in the UK. So this is freely available at that link. You don't need a login or anything like that. You should be able to access it directly. You will find there are some additional resources on the website, and they generally will require a login or will require a fee to be paid at company level. That's things like code lists and guidance and so on. In fact, in theory, you do technically need to register to be able to use the format. So now just going to talk a little bit about, I guess, some complementary additional formats, because AGS has grown in recent years. And we'll start with one I mentioned briefly earlier, which is AGSI. And this is a separate new format for ground model and interpreted data. It is live. We've at version 1. It does differ quite significantly from the AGS format in that it uses, I guess, a more up-to-date sort of object model approach and JSON encoding, and the documentation is basically a website. And our current focus there is very much on implementation, both in terms of projects and in software. We do have an early adopters group set up, and if you're interested, you're most welcome to reach out and get involved with that. And then we also have something called AGS piling. Now, this is a little bit behind AGSI. We have got a fairly mature draft that's already been issued, but not quite reached beta status. We have got a working group that's formed just under a year ago. In fact, we had a meeting this morning. So this is led by the AGS, but also includes significant membership from the FPS, which is the Federation of Piling Specialists. That's a similar group to AGS, but for piling. And also there's also interests from the Deep Foundations Institute as well. And the idea with AGS piling is it will include primarily the construction record, as built details, all the logged or measured data from construction, pile test data, of course, but also design schedule information. So returning to the main AGS factual data format, where may it be going in the future? Well, first of all, probably the first big thing you'd like to see next is AGS version 4.2, which is expected to include an overhaul of the CPT and pressure meter testing tables to address some issues with those. In fact, there's already drafts of those out for comment. And also looking to introduce some advanced lab testing for the first time as well. Now, in terms of some of the topics that have been just discussed within our group, we are looking at alternative file formats, maybe JSON, maybe not, we'll see. So it is on the radar, but also on the radar is APIs. And what does this mean for AGS and the AGS format? Because we are seeing people using APIs for dealing with geotechnical data at the moment. Now, we think that if we do nothing, it potentially might become a bit of a challenge to us, but we can also see opportunities if we're proactive on this. So that's what we're looking to try and do at the moment. And then we have AGS 5. So this would be expected to be a major update. There's no particular timeline at the moment, but we are now seriously discussing it. In fact, we have a quite major meeting on it coming up in May, where we're looking to really try and nail down the requirements and objectives and go from there. So obviously AGS doesn't exist in a bubble, so thinking about interoperability. First of all, we've participated, as Mickaël has already mentioned, in this OGC Geotechnical Interoperability Experiment work. And as part of that, we were able to find that we could map AGS to the conceptual model that was developed. That revolves around the book A stuff for the investigations. Although we do find that most of our data in most of our groups actually ends up as observations in the conceptual model. We also had a look at mapping to the SensorThings API model, which could be done, but there are difficulties there because we end up with the AGS group data being split across many different objects, so it's not necessarily straightforward. One thing which is point out is when we were looking at doing this OGC work, the idea wasn't necessarily to develop a format to compete or replace AGS or indeed DIGS, which you'll hear about in a moment. And in fact, the work that was done was very much leveraging our existing and extensive and well-developed data dictionaries as part of that work. Now, IFC, which you're also going to hear about today, is an interesting one. Now, we actually think that this is where AGS data can be a complement here, in that it could be a linked data set, because AGS data is good for structured data, not so good for complex geometry, whereas IFC can perhaps turn it around, good on complex geometry, not so good on structured data. So maybe AGS can exist side by side as a data set. That may be something that Jonas may pick up on. So that's all I was going to say. And despite the interruptions, I'm almost on time. So just a few headlines just to sum up. AGS data format, it's well established, and I can't stress this enough, it is very well used in the United Kingdom, so it's real. It's getting on a bit. It maybe looks a little bit old-fashioned in how it does things, but it's a relative simple structure and file format, and that has served us well. The AGS data format itself is for factual ground investigation data, but we do have this new AGSI format for ground models and interpreted data. And we also have AGS piling under development. And you can see that we have also been developing some links with IFC and also with the work of the OGC as well. And finally, if you want to find out a little bit more about AGS data, then obviously you could go to the documentation. That would be a good start. If you want to go even further than that, there are training courses that are available. They're not official AGS courses, they are commercial. But if you search for AGS data format training, then you should be able to find them. If you're interested but are struggling to find them, then you're welcome to reach out to me personally. So
thank you very much, Neil.
That's my presentation, and I think the idea was we're going to have a few minutes of questions if there are any on Slido.
Yes, we had some questions. Thank you very much, Neil, for this overview. So we will try to find interesting thing. So there are questions about advantages between AGS versus DIGS versus IFC. So I would say that you will have an overview of what DIGS and IFC can do for geotech soon. So I will just maybe transform that question to Neil to just what is, in your opinion, Neil, one of the best thing that AGS do, main advantages of AGS? Why is it so successful?
Why has AGS been so successful? I think, well, first of all, one of the reasons it developed was there was a clear demand in the way that we work in the UK. So that's one of the reasons why I think it's been able to be embedded. It didn't happen overnight. It did take many, many years to get there. I think it's success. It's simple, and it makes it relatively accessible, I think, or that's what I would say. And I think I sometimes look at some of the other things that are developed and think they're more for data scientists rather than geotechnical engineers. So there's always an interesting debate to have there. We could probably debate that one all day, but I think that's one of the things that I would say. We've been quite stable as well. In fact, there is an argument that we haven't updated frequently enough, but it is useful to have some stability so that people can work with it, and in particular the software that's developed to support it. I mean, if the software hadn't supported it, then it wouldn't have had the success it has.
Thank you, Neil. There is another question: is why didn't you go as I would say standards like having ISO certification or something like that?
Oh, well, I've got to be a little bit, maybe I've got to be a little bit careful about what I say here. And also, I don't necessarily know the background, although there has been some discussion of this within AGS recently in a different context. My understanding is it was discussed, but we're talking about 15, 20 years ago. And I think a concern at the time was that I wasn't around at the time, so I'm reporting what others have told me. But firstly, if we'd gone down the BS or ISO route, AGS would have been required to have changed the format in certain ways and move it to marry in with other data formats. And it was already fairly well established, so there wasn't very much appetite for that. And also there's a matter of control as well, because it would have led potentially to losing a bit of control. So there is a trade-off between control, but also having that status of a BS or an ISO standard. Now, in our case, it's worked out absolutely fine, because there is one advantage, which is maybe not immediately obvious, but AGS can make this available for free, the documentation, whereas people have to pay to view ISO standards and BSs and things like that, albeit companies tend to pay for that. So that is actually, in our industry, that is actually a significant factor. So yeah, and that's an interesting one, but that's it. There was a conscious decision made a few years ago, and for AGS, it's worked out fine.
Okay, thanks. So there are other questions that are more about especially contributing to a GSI, if I understand well, and also another one. Yes. And yes, how to address triaxial. So maybe this one you could address it directly in the chat. It's not an easy one to answer, I suppose.
Yeah, there's specific questions here that it may be easier for me while I'm watching some of the others to actually maybe do that. Yeah,
so you can have a look
I don't want to get into an argument now about AGS over digs as well, given that Dan is coming up to talk about digs.
Exactly, and you will have an overview of what is digs and also what can be, IFC can offer, and also a question about what is book A in the context of data mapping. So book A is about geotechnical investigation. That was the wording we use. Maybe I think Jonas will come back to it in its presentation. So I propose to move to the presentation of Dan now about digs. That was built upon AGS at this time. So Dan, if you are here, I will propose you to share your screen.
I am here, and hopefully we can get the slide presentation up.
We have some orange flow. Oh no, we have your presentation. Digs that
we have the presentation.
Yes.
Okay, I didn't realize we were going to get into a knockdown drag out fight with AGS, but it's certainly not the intent, and actually digs owes a lot to AGS in terms of its origin. Thank you, everyone. For me, it's a good morning, good afternoon, good evening for the rest of you. My name is Dan Ponti. Have been involved with the DIGS project essentially since its inception, and has been one of the folks that has been involved in a lot of the schema design. My background is actually in geology, also in engineering geology. I was a research scientist at the U.S. Geological Survey for about 40 years, almost 40 years, and got involved in the DIGS project in part because of some desires and needs on our end to begin to standardize borehole data and other types of geologic and geotechnical investigations. So that was how I sort of got into this, and I feel very strongly about trying to promote these sorts of standards. So I've continued to be involved in it even after I left the survey. So the overview of what I'll talk about today is kind of a similar format to what Neil had done. What is DIGS? I'm going to talk a little bit about current implementations. We're not as far along in terms of implementation clearly as AGS, but things are beginning to kick off. I'll talk a little bit about the data model, what exactly DIGS does, what's in it, how it's organized. Some recent extensions that are taking us out of the ground investigations mode a little bit and extending that. And also some of the current and future efforts that we're into, and then a little bit of discussion about DIGS and our involvement in the Geotech IE. So what is DIGS? It's a US-based transfer standard similar to AGS for geotechnical and geoenvironmental data, as opposed to the sort of flat file CSV sort of format that AGS uses. Ours is an object-based XML schema with associated XML dictionaries for test properties and code lists. It is built on geography markup language, the GML, the OGC standards for defining vocabularies for geometries and locations of features. And so that's sort of why we're wedded into XML. We also incorporate some other XML vocabularies as well. The GML 3.3 extensions that bring in linear referencing and vector types. Then we use this for developing local coordinate systems for boreholes and other types of what we call sampling features. I'll get into that a little bit later. We also use some parts of the WITSML standards. This comes from Energistics. This is an oil industry XML vocabulary for their drilling work. And what we use from them is their measure types and unit symbols. They have defined quantity classes according to different types of measurements. So we can define, for example, a pressure measure and be able to hone in on the on appropriate unit types for pressures and be able to validate that within the schema. So we found that to be very useful. So we've incorporated that as well. A lot of our structure and object structures are influenced by OGC's observation measurement standard, the earlier version 1, which was around when we were building this, and the GML coverage models for our observations. So we're leaning a lot on existing standards. We are open sourced. We're largely volunteer developed. We do support AGS4 groups and headings. One of our goals was to be able to interoperate with AGS and be able to accommodate information that's in the AGS standard. And we support both exploration, ground investigation data, and construction activity information. A lot of DIGS originated about in the early 90s from efforts that were underway in the highway transportation realm, and as well as earthquake engineering, in terms of trying to disseminate information in a standard fashion. There were all sorts of ways of doing that back then. But DIGS as an XML standard really started in about 2004 with a pooled fund study that was funded by the Federal Highways Organization Association in the US. There was an initial 1.0 version of DIGS that was created in the early 2000s that was not very usable. It was clunky. It wasn't very well designed. So that got revamped in part under the auspices of the American Society of Civil Engineers, their Geo Institute. We became a special project around 2012, and ASCE is now the Geo Institute is now the sort of overseer of DIGS, and we do get a little bit of funding from them through their special project program to do some of the development work for the standard. The first sort of stable production version was released in 2020. That was version 2.5. And we've just released a new update to that, which is includes a lot more it's a richer data set, a lot more test procedures associated with it, as well as extensions into construction activity information. You can find information on our website at digsml.org. All of the fun parts of the dig standard are all hosted in a GitHub repository, the digsml. So the schema repositories are there. There's documentation and other resources. And we're working on revamping that and getting a lot more documentation online. So the goals of DIGS when we were developing it is we wanted to develop a standardized structure for geotechnical data that leveraged existing web-based technologies as much as we could. We didn't want to rely on any proprietary software or systems. We wanted something that could be readily validated, parsed, and queried and transformed to other formats with existing tools. So some of the difficulty that Neil had mentioned, it's difficult to parse AGS standard because you need to have specialized software for that. We wanted to see if we could take advantage of existing tools and use formats that would allow us to do that and not have to worry about it. We wanted to be able to accommodate more complex data relations. AGS's simplicity also has some limitations. We wanted something that was flexible enough that we could accommodate different standards of practice and data detail. And so most elements are optional. There's a lot of stuff in DIGS that you don't need to use, but it's there if you need it. We also wanted it to be extensible such that we could add to the schema as needs expanded without breaking what we already existed in terms of its design. And it's also profilable, which means that you can take a dig schema and customize it to your needs within limitations. You can make optional elements mandatory. You can remove optional elements you don't need, and you can sort of tailor it to your specific needs if you desire to do that. So what we wanted to do was with this is accommodate a wide variety of practice in languages, units of measure, et cetera, and not dictate practice or change workflow processes. This is just designed to be a pipeline to enable the transmission of information from one system, one organization to another, much as Neil had shown that AGS is used for. In terms of current implementations, one of the things that happened with our 2.5 release in 2020 was that an organization in the US called AASHTO, which is an American Association of State Highway Transportation Officials. It's a big standards body in the US involving around highway and road construction, has made DIGS now a provisional standard of practice for the dissemination of geotechnical data. So that's piqued some interest from vendors and departments of transportation in terms of how best to move into a better, into more standardized digital interchange of data. One of the problems that in terms of getting going, and I think Neil sort of touched on this a little bit, it took a little bit for AGS to go, is that there's sort of a chicken and egg problem. If you're a user of geotechnical information, why should you export things or move things around in DIGS format if there isn't any software to support it? If you're from the software vendor side, why should I be developing support for a standard that nobody's using? And until that sort of breaks, things are a little slow to get going. But that's starting to happen now with DIGS. Rock Science is a software product that is used for borehole log display and implementation. They now have developed a module to import DIGS into their system for producing borehole logs. 4DM in a similar fashion, only they support both import and export of the DIGS format now. There is this GRL Weep is a piling analysis application that has in their new version 14 will be able to import CPT and SPT along with some other ground information data into their analysis software for geotechnical characterization in their analysis software for piling data. GeoComp now has export of their triaxial test data. Tablog is another boring log and data collection software package that can export into DIGS. And Data Forensics which is a small software company that builds tools for Open Ground, for Bentley's Open Ground, has developed an import converter service to take DIGS information and be able to bring that into the Open Ground cloud. So we're starting to see fairly rapid initiation of acceptance of the DIGS format from a number of different vendors, and these things are coming online. If they're not already online, they'll be online very soon in advertised releases. And this recent uptake in the vendor software support really comes at an opportune time, because it's a lot of the U.S. state departments of transportations are moving toward digital project delivery at a fairly rapid pace. So this is likely the driver that defines sort of the purpose and need that really didn't exist much in the past, when individual organizations had their own workflows operating, and there didn't seem to be much desire or need from their parts for this sort of cross-platform standardization. So things are kind of interestingly coming together and have been over the last couple of years. Another application that's been interesting is a web-based product from an organization, nonprofit called GeoSeta. GeoSeta is compiling and collecting historic geotechnical information primarily from departments of transportation, from other sources across the U.S. They're integrating that information with soil map data and groundwater data. And DIGS is the mechanism by which that data moves in and out of the platform. You can go on there online, you can pick out sites, you can generate both boring logs and tabular information from the DIGS data on the fly on the website. But beyond that, they're also beginning using this information with machine learning tools to do predictive analysis and make estimates for soil characterization, SBT estimates based on these data that are being collected. So this is one of these interesting applications when we begin to be able to standardize these data sources to be able to utilize massive amounts of data to feed into machine learning and AI projects for looking at really interesting predictive applications. So this is kind of a cool thing that's also beginning, and DIGS is the pipeline for all of that information. So the DIGS data model. So a DIGS data file, or what we call a DIGS instance, is simply a collection of XML objects. And if you're not familiar with XML, this is an example of what it kind of looks like. This is actually an example of some information that describes some lithology data within DIGS. The fundamental element is a thing called an element, which is basically structured text that has a tag that's enclosed in the angle bracket. So this tag here is legend code and a value associated with that, here called silt. This is sort of the fundamental piece of an XML element. You can also have data within the tag. We call those attributes. There's no real rule in XML as to what data can go into is in the element and what data goes into the attributes. We use it primarily for metadata about the data. In this case, this attribute defines an identifier for a particular XML element. We also use identifiers a lot as pointers to resources. This particular element classification code identifies a type of lithology. It's called the sandy silt. And this URL that's sitting here in this code space attribute is a pointer to a dictionary definition of sandy silt associated with the ASTM standard for unified soil classification. So DIGS doesn't tell you how to define geology, but it wants you to tell other people where that information comes from. So this is done through these code space attributes and dictionaries, which DIGS is developing sets of those as well, but they can also be your own dictionaries. So we're not telling you how to do things, but we ask you to tell the rest of the world as you transfer this data how that information is defined. Obviously, also elements can have other elements associated with them. So this lithology element contains a bunch of other elements incorporated within it. And when we have a complex element like that, in DIGS speak, we call that an object. So that's our XML object. And then in the context of that, the elements that are part of those XML objects are what we call properties. So the properties of this lithology object include things like its description and its legend code and the classification symbol and classification codes. So what a DIGS element, a DIGS instance looks like is just a collection of all these different types of objects that can be fairly complex with objects within objects as well. And so we have this sort of flat level DIGS data model from which every single one of these objects fall into one of these boxes, which we call object classes. So an object class is actually a type of or a related set of DIGS objects that all inherit from what we call an abstract type, a type of XML object that has properties that are common to everything within that class. And those classes are associated to each other by referencing properties. So rather than having a hierarchical top-down structure like AGS has, we have more of an associative structure between the different types of objects and how they're interrelated. I'm not going to go through all these in a lot of detail, but I'm going to talk about a few of them. One of the important ones is what we call a sampling feature. Sampling features are physical objects or locations through which we make observations or from where we conduct an activity of some sort. And what it does is provides the frame. It's essentially a viewport into the world, and it provides the dimensionality and the scope of the area that we're looking at. And it also allows us to define a reference system that can locate observations within that sampling feature in a more convenient fashion. So as an example, if we're kind of thinking about the world, we've got the target. If our target is the natural ground, and we have a series of different kinds of targets, but let's say we have a natural ground target, we sample that natural ground target through sampling features. One of those happens to be a borehole. And I'm showing an example here where we may have a borehole where we excavate into the ground, or we have a trench wall, or we have a face cut into that surface. Those have specific types of views into the world, and we model those in different ways. So if we just look at the information from a borehole or the information from a trench wall, our understanding of that target in a borehole is essentially one-dimensional. It's a linear object, and we can locate information along that linear object by distance from some origin. So that's their depth, measure depth of borehole, standard kinds of things. If we look at something along a trench, we can identify observations within the trench wall in 2 dimensions. We have an X and a Y or an X and a Z coordinate that identify locations within those things. So we classify these sampling features by their dimensionality. Those carry properties that define how that define the shape of those features, and also how local locations can be locally referenced within that feature. So we do a thing called local coordinate referencing or linear referencing, which allows us to define locations in a more simpler fashion than an absolute coordinate system. So if we look at a borehole, for example, we have 2 geometries associated with the borehole. One is the reference point, which is essentially the origin or the collar of the hole, and the other we call a center line, which essentially defines the borehole's trajectory. And that's a line string that has vertices that are defined in a real-world coordinate system in 3 dimensions. And then we can define an object that we call a linear spatial referencing system, where we can define the linear element of that as the center line, the reference, which would be the reference point of the origin for that line, how the measurements are made, which typically is absolute measurements from the origin, and what that unit of measurement is. So we can say that we want to have a unit of measurement in meters. We're going to track along that borehole, and then we can use that object as our spatial reference system when we define a point. So if we have a sample located, say, at 4.2 meters down the borehole, we can have this point location object that defines that location, and it points to the spatial reference system that we've defined for the borehole. And that tells us that 4.2 is down the trajectory of the borehole, and it's in meters. We can expand that from 1 dimension to 2 dimensions by looking at something like a cross section here, or a trench section, where we define a couple of other geometric features. We have a reference point. We have a reference edge, which is essentially equivalent to the center line. That's the red line in this diagram. And then we have a polygon, or a series of surfaces, or series of polygons like we would here, that defines the extent of the actual feature in two-dimensional space. And then we can define things within it, either as polygons or lines or points, like the fault or a sample location or that geologic unit that's pointed out there. And then we can define a spatial reference system with that as well, but we add another component to it besides the linear element and the referent. We add a thing called an offset vector, which defines the second dimension direction. So we use a unit vector. In this case, we're looking at a vertical cross section. So the unit vector says that all we've got is motion in the z direction. But you can change that unit vector coordinate system any way you want to, and you can rotate that surface and define any sort of orientation, whether it's vertical, horizontal in the map view, or anything different from that. And then we have another extension to that adds another orthogonal vector type to it to define three-dimensional volumes and three-dimensional spaces. So we're going kind of beyond the idea of the single borehole. It's all encapsulated in the sampling feature. Finally, we talk about sampling activities. I'm going to go real quick because I'm running behind. But we separate the activities of samples from samples themselves. Trying to get this to work. I'm going to skip through this, but basically we can define a sample activity that gets samples. That activity produces a sample or several samples. That's what the activities do. We then can subsample from those through another activity, and then those samples potentially can turn into specimens for laboratory testing. Specimens are not samples. They have different properties that are associated with the test measurement themselves. Also in our conceptual model, we have two ways of defining observations. One of them is called a measurement, and the other is called observation systems. Measurements are used for numerical information that's largely derived from testing equipment or sensors. So laboratory tests and situ tests use this. We have a defined structure that's modeled after the GML coverage models, or these specialized measurements. One is called a test that identifies measurements or results associated with spatial distribution of data. So that's used for things like CPT tests or standard laboratory tests. We have a flip side one called a monitor, which uses a temporal domain. So that's used for our monitoring measurements. Those have similar structures, and then they're associated with a procedure object, which defines the metadata and intermediate observations and results for those tests. We currently have 61 of those laboratory test procedures defined, 16 in situ test procedures defined, some general procedures, and we have a dictionary that defines the observed properties. There's 349 of them currently in our dictionary. Observation systems are defined or used for direct human interactions, observations that require judgment or analysis, typically category data. There are different specializations for those, but these are the types of information that typically go into borehole logs that are descriptive or interpretive. Things like soil classifications, stratigraphic designations, color descriptions, geotechnical unit determinations, those sorts of things, identification of faults, those sorts of things go into structures that are part of our observation systems. So those are the two types of measurements. We're developing some extensions to handle geophysical data. The challenges here are the massive amounts of information and some of the complexity of the raw data. We do this two ways. One is to define the process geophysical data. The final results are done in, it uses our test object like every other measurement. We've developed a procedure object to report the processing steps for that. And we've added some pieces, some sampling feature specializations and some geometries to enable more compact encoding of that information so that we aren't blowing things up, as well as defining some spatiotemporal coordinate referencing systems for things like seismic time series, or I'm sorry, time sections or time volumes. We've also have those structures for 2 and 3D, and then we have a container object for carrying raw geophysical data and a procedural object that allows us to represent the metadata associated with a field survey, including source receiver geometry, source receiver configurations, and those equipment types. We're also getting into construction activities. These include primarily grouting right now, and we're moving into piling construction. We have 2 object classes for that, one for describing the construction activity, and then the other one we call a program, which is where we specify design criteria, specifications, and performance specs. We've done this now for grouting. We support rock permeation, compaction, and soil mixing. We have a series of grout sample test procedures associated with these. The program components include grout mix design and grouting specifications and performance specs. We're currently working on developing data structures for measurement while drilling data, driven pile installation data, and as-built driven pile information, along with code lists and dictionary developments and API development. So finally, we've been involved, as AGS has, with the Geotech IE, where we're involved because we want our system to be interoperable and we want to learn what other folks are doing. So it's important for us to try to maintain interoperability with other standards and systems, and to align our structure with the OGC conceptual models for boreholes and sampling features, samples and specimens, and the like. And we're quite successful in being able to do that, in large part because DIGS incorporates a lot of these OGC concepts in its structure. And so we've contributed object property definitions to this effort, measurement property definitions, and as well as developing requirements and helping to extend the OGC Sensor Things API to be able to accommodate these data. And we've been successfully mapping to and from that system. So that's it. Thank you very much. And if there's time for any questions, I'll take them. Otherwise, we can do it later.
Yeah, thank you, Dan, especially for attending this meeting at 5 in the morning for you. As you said, yeah, we are a bit out of time, but I will take one question that was about why did you choose XML? I think there was a question about why XML versus JSON, but I guess it was just because there was not so much JSON at that time when you did work on it.
There wasn't JSON at that time, and actually, because we wanted to leverage the geometry definitions from GML, that was letting us to XML. Actually, the way DIGS is structured right now, I think XML is still the best format for it. JSON does have some limitations. It doesn't handle namespaces easily, although that's becoming better developed. At the time, there were no JSON schemas. That's changed, but there's still a lot of there's a lot more flexibility in the structure with XML that I'm not certain that we'll be moving to JSON soon. But as JSON continues to develop, that might be something that we'll move toward.
Okay, thanks. So I will propose to move on and welcome Jonas. Jonas, if you're still with us, I will propose
I am still here. Hello.
Fine. Hello, Jonas. So same as Neil, same as AGS, people want to know about IFC. Oh.
Let's see what I can do. Good afternoon from Austria, and hello to all the other time zones. I will start sharing my screen if it works. Here we are. Now I need to organize my windows, and here we go. Okay, that's the final one.
Yeah.
Yes, I can tell you a little bit about the IFC Tunnel project and the initiative to include geology and geotechnics into the IFC scheme. Starting with the motivation, of course. As most of you know, in tunneling or other infrastructures, you're dealing with these challenges of large volumes of data, big complex sets of factual data especially. You need to translate your geological models, geological conditions into geotechnical models that are adequate for certain design issues. You frequently need to verify your models when additional data are coming in. And of course, the infrastructure projects are associated with high cost for the construction, or the ground conditions are responsible or limit or define the cost for the projects, and there are a huge factor of uncertainty. This is the reason why it is many of the infrastructure owners are aware that they need to pay attention to this, and as they develop their digital tools for design and develop BIM models and digital twins and so on for their buildings, for construction, design, operation. Also, the ground conditions came into the focus. So I start this from the other sides, because IFC, of course, was not developed for ground models and geotechnical data, but it came from the other side. It came from the design side. So I think to all of us, why we need ground models and why we need data structures to handle our data, they are clear. But why IFC? IFC is the standard, established standard in open BIM projects in many parts of the world. One benefit is that it includes the geometry along with properties and a detailed semantic model for buildings and many other things, equipment and so on. So far, ground models have not really been supported by this scheme, but however, IFC is frequently used already, or IFC ground models are commonly requested by infrastructure owners because they say, we are doing the project in BIM, we use building information modeling, so please give us your ground model in IFC that we can include it in our common data environment. So far, all these requests need to be answered by custom solutions, proxy elements, and using existing schemas to include the geometry and the properties of the ground models. And this puts, of course, big limitations to these models and to the applications. In these BIM projects where the ground model comes in via IFC, they are frequently or usually only used as the background models. So there's not much model-based workflows or model-based interpretation analysis on IFC ground models so far, from my experience or from the experience of our group. But we think that this can be changed if the IFC scheme supports geotechnical data and becomes more established also in the software landscape for ground modeling or our domain tools, let's say. Of course, there's no intention to replace these established formats that we just heard about. That's why I started this introduction from the other side here. There is this request to bring ground models and geotechnical data into the BIM world, and IFC could be one vehicle for that. One argument is that many of these standards that we know, AGS, DIGS as examples, are not designed or not so strong on the geometry side. So let's have a look on this, or overview on this project. What is happening at the moment on the IFC side in the course of the IFC tunnel project. The project started with a requirement analysis where domain experts, me, Mickaël, and many others also joining this call today, developed, we wrote this requirement analysis report that maybe some of you know, defining use cases, defining typical exchange scenarios for geotechnical data and ground models. And on that base, the taxonomy and the conceptual model have been developed. Of course, this went along with all these coordinations with people from very different backgrounds, from very different initiatives, sitting together on the table, bringing in what is already there, bringing in their personal experience, bringing in contributions from all parts of the world, and trying to develop a conceptual model or set up a conceptual model that reflects, on one hand, the the workflows that we think are relevant according to the requirement analysis, but also takes what is there from these existing standards, like AGS, DIGS, and so on. So this was the big activity of us domain experts, let's say, and the goal of this conceptual model was reached by end of 2022. 2023, the draft of the schema extension was shared with the technical team, was shared with software vendors in the course of the deployment program. And at the moment, this is the implementation of this conceptual model to the schema is happening. And I will show you in some slides later where you can have a look into these draft versions. So the focus for us, according to our requirement analysis, was a few points that you see here. We said, this was a discussion before, should factual data be included or supported by IFC at all? Because there's existing standards, maybe it's not necessary to exchange them in IFC, because the question was if it's really necessary to bring them into the common data environment of a huge infrastructure project. Who wants to see the geotechnical tests in there? Yeah. One argument to offer this option was, of course, the visualization, that you have a format that supports 3D and can be easily imported to show where is information, where does information exist and where not, where are the gaps. And another point or another idea was to maybe widen the range of tools that can be used to make spatial analysis, geometrical analysis in 3D with all these tools that are developed for BIM models and so on. When you have the ground or the geotechnical data available in IFC, many other tools can use this, and people can develop their custom workflows for further investigations, for further analysis and so on. Then one goal was, of course, to support geotechnical models for design. And we also agreed in this domain team that broader or more general geological models are a most important source for us when we develop a certain model for a certain design case. So we want to support geological models as well as very specific geotechnical design models. And another goal was to link the ground model to the building model. So to use the model to describe the ground building interactions and to use it for prognosis and as an import for design applications. So this is illustrated in this slide here. You see again these books that appeared before that Mickaël mentioned. They came from the French standard and established in our group in the last years. But not only there, but also in several other publications. So we think it's most important to distinguish what are observations, what are factual data, and what is interpretation. Of course, the interface is not always clear. There's always a certain interpretation included in the observation, but we need to express this somehow in the model or to structure our model accordingly. So factual data typically include all kinds of geotechnical testing, field mapping. Existing literature can even be imported or linked. Monitoring data are an important source, and they all should be represented somehow in the or should be supported by the IFC schema to show what the database actually is before you do the interpretation. Then the interpreted models include not only geotechnical layers, but also geological aspects. We go into detail on that. And with this example for a tunnel, we think it's most important to show the connection from a volumetric model to, for example, a linear structure like this tunnel, and to have a design-related prognosis model, to have a design-related element in your model scheme that describes certain conditions specifically for that building. So this is the model to describe the building ground interaction. And this is the one that can be used for further interpretation or for further applications like contractual topics, time, quantity estimates, and costs. So what are the most important aspects in those models according to our analysis? We think regarding observations, we made a collection of typical data that we think are essential to be supported. We also had to exclude some things, or to, as I said, we put a focus on certain things, and we had to bring it on a certain level of detail that is adequate to not overload the IFC schema and to not interfere too much with these existing standards. Then we needed to decide which elements or which information should be linked to an object, what are actually the objects that we model, and what are other elements like semantic elements that do not necessarily need a geometry. Then most important for us not to overload the schema, but give a chance to link external files, to use IFC as kind of a front end connection to the design model, visualization tool, but have the chance to include very complex data sets. And then one thing that is already applied and that is commonly used in IFC are custom property sets, because of course we cannot define all necessary properties to describe certain tests, certain aspects that might be relevant in a project, in a country, according to a certain standard and so on. For Book B, as I said, we wanted to have parallel models, because of course you can classify the ground according to certain aspects. You can have a stratigraphic geological model, you have a model of tectonic structures, you can have a hydrogeological model, and you can have a geotechnical model for a certain design case, but you might have a different geotechnical model for another application. And of course, it must be possible to have multiple models that describe the same piece of ground. So this was one condition. And then I mentioned before, this geotech synthesis model was our intention to define a link from ground model to building. So what's the status? This conceptual model has been completed, as I said. Currently, the tech team is working on it along with the deployment project where the software vendors are included already. The goal is to deliver this proposal in the course of this summer, and then the Building Smart International Board will need to review and give the approval. This is expected to happen in end of this year. If you're more interested in this process and the status, you can use the link below. The slides will be shared, of course. So let's have a look into the content. Let's see which elements we have defined now. Starting with Book A, with observations and measurement results. There are different kind of objects. The first one that I want to show you are these, let's say, containers. The spatial elements that actually describe where certain observation or measurement has been made. Yeah, typical example would be a borehole, of course. It can be mapped zone or a tested zone, something where certain method has been used. You might be aware that IFC 4.3 already included a simple concept for ground models, including boreholes. The shortcoming from our perspective was that this scheme included only interpretation that are actually then mapped on a borehole to say this part of the borehole belongs to a certain interpreted unit. And we said we need to support Book A. So we changed this definition. We changed the semantics, but we keep this IFC borehole element from 4x3. And we established the possibility to include observations to this object. So there are many options now how to attach your information to the model. The simplest one that is commonly used already is to model only the borehole in 3D as a cylinder, show in a common data environment, look, we have a borehole here. Then you include a hyperlink into the properties, and somebody can drop certain files on SharePoint or wherever to query it. Of course, there's much more sophisticated methods to do this in IFC, and this shall be supported by the schema that external files can be linked to borehole objects. But it should be also possible to go into more detail and model the logs or the observations that have been made along the borehole as 3D objects, and to attach property sets for logging data. Yeah. So the scheme that is in the proposal now includes a standardized slim set of key properties that are usually logged. But as I said before, most important is the option to use custom property sets, because logging is never, or borehole log is never performed in the same way all over the world in all the projects. There's a lot of software-specific, country-specific, standard-specific, geology-specific aspects that you need to log, and it must be possible to use this to define the properties of the data you want to add to the borehole log according to your needs, and it should be possible to map these existing standards to map existing data dictionaries like AGS or DIGS or other standards into such custom property sets. To use IFC really as the front end, but keep the data structure as it is in other standards. I linked at some occasions here the guideline that has been published last year by the German DAUP. That's the German, Austrian, Switzerland branch of the ITA, because this was one of these initiatives that was running parallel with IFC Tunnel, and we adopted a lot of the thoughts from IFC Tunnel into this guideline. So it might be interesting. It's available in English and in German, and you can have a closer look at this, especially regarding this granularity level of models that is described there. So now let's go to the measurements themselves. So we mentioned before the containers, the spatial objects. Now there have been some observation types defined, starting from borehole log, measure Weil drilling interval, certain tests, certain observations that are made during field mapping. Of course, this does not cover all kind of observations, but it's on a certain on a high enough level, I would say, to include most of the observations that you can make, because as I said, you can model this and then you can define your custom p-sets to further distinguish what has been actually observed or what test has been performed. I will get there in a few minutes. Another example is tunnel documentation, because we said, of course, for IFC Tunnel, it's not only necessary to include the information that is collected before the project, but also during execution, include the documentation inside the tunnel and make comparison of predicted versus encountered conditions. So you can say that the tunnel phase is actually an area where observations are made. It's a mapped zone, according to this terminology. And on this mapped zone, you can measure discontinuities, you can measure certain units, lithologies, you can measure water inflow and so on. So any of these observations can have a geometry but be linked to the spatial element. So this can look like this. You have the tunnel face itself, then you have two mapped units, one part here, and then you can, of course, draw in more detail and include traces of discontinuities, overbreak, and so on, and attach these geometries to your mapped unit and to your tunnel face. So now more details on the test results. We said we cannot copy existing data dictionaries, and we cannot go into very detail and define 10 different types of stiffness or elasticity modulus, deformation modulus, static dynamic modulus, and so on. So there has been a lot of discussion how much properties shall be included, and we agreed to do this rather exemplary, how to say that in English, to define some example properties that show how the model elements can be used. For example, we said we can have a p-set for dilatometer tests, we can have a p-set for CPT, for SPT, but just with a few key properties. Use these key properties as they are included, or the definition and terminology, use this from existing standards. So any user will see how we can use this observation and this test result elements. So if we go into the documentation now, you will be able to use this link when you get the slides. You can jump with this link to the Building Smart International homepage, and you can go to changelogs up here. You can scroll down and you can look at new entities that have been included in IFC 4x4. And I would like to take this example to go to GeoScience observation. So you see, this is the definition of GeoScience observation, detailed collected information, including measured parameters and so on. And here you see that there are certain IFC GeoScience observation type enumerations. You see that there are several types of observation defined already. This can be a borehole log, this can be a mapped feature, it can be an in situ test result. So this is the level in the scheme where the kind of observations are defined. And if you want to go in further detail, if you want to describe what kind of test has been applied, you can add accordingly the relevant property set to this test result element. And the property set would be, for example, an in situ test CPT. And what do you see? Very thin. There's not much details. It just says cone resistance, side friction, pore pressure, Yarn's modulus. And there will be a few more of such tests supported, but the intention is to leave this open because we cannot try to copy the data dictionary from AGS and include hundreds of tests and hundreds of properties for two actual tests and so on. But we just provide the interface where this data and this where this information can be connected. There's also one piece set, a common one, to say for many observations you need the same records independent of the test to say at which depth of the ball has it been performed, what was the method, what was the type of test, and so on. There are more common P sets to describe date, time, who worked on it, what was the purpose of the test, and so on. Going back to the presentation. If you want to go in more detail and see what is actually being discussed, how were the decision made, or what is still pending, because you will see that many of the of these elements that I showed in the slides of the conceptual model are not available yet in this schema documentation. But you can go to GitHub, and this one is also available to the public. And you can search for certain points in the issues, and you find, for example, what was commented, how to deal with IFC borehole, how to deal with IFC geoscience observations and science features, and so on. And there's a lot of details. You can participate in the discussion, and you can see what is behind this concept that the technical team actually used to prepare the proposals to Building Smart International. No time to go into more detail on that. So back to the presentation. Here we are. And let's go to Book B, to the interpreted models. For those, we said we need to distinguish several kind of classifications. So we have 3 parallel concepts now. You can have a geology model with certain geology elements like a geological unit, a fault, a contact, or even a fold structure. Those terminologies or those terms were mostly adopted from GeoSciML. Then we can have a hydrogeo model. This was also aligned with GeoSciML. And you can have a geotechnical model where we distinguish actually 2 features, a geotechnical unit, which would represent, for example, a layer, a certain volume, or you can have a discrete discontinuity that might carry discontinuity strengths properties like friction angle, cohesion, that is relevant for a certain feature that is really modeled in 3D. So this is again an overview of these units. You will find all of them in the documentation on Building Smart International homepage that I showed before. And I want to pick out one that is most relevant for the geotechnical engineers and for the designers. So we usually provide a geotechnical model specific for a certain project, for a certain application, and we define ground properties for the design. And for now, the scheme includes 3 approaches to describe the properties of such a layered unit. One is a property set for soil-like materials with key properties for soil. Of course, this list can also be endless depending on the material models you want to apply in your geotechnical analysis and so on. But again, this would be the approach to use custom property sets. The second option is description of rock material. And we said typically in rock, you need to describe the intact rock properties, you need to describe the discontinuity properties, and usually you have rock mass parameters that you use on a larger scale. So there's 3 property sets for these type of units. And then we said it might be helpful to see the rough idea of your materials in the model, but usually in tunneling, you cannot predict in detail where these materials are. So you have a rough idea from the geological model, but you cannot say this ground type is here with 2 meter thickness and so on. So this is again a concept of model granularity. This third property set, or this third approach that I showed, actually allows to describe the distribution of certain materials just in the semantics, and your model could look like this. You have a detailed model close to the portals or in a certain area of high interest where you have more knowledge, where you have more investigation data, where you model your materials in detail and define the geotechnical properties. But for most part of the tunnel, you will not be sure, and you just say, in this part, I have a certain distribution of, I don't know, 60%, 60 to 80% of this unit and of this material, and the rest is the other material. Yeah. So this can also be handled in the properties, but you can give your designer an idea what to expect. This links us to the topic of uncertainty. as you know, in all of these work groups, you end up in discussions about uncertainty and how to handle it and how to classify it and how to transport it. And we all know that any model is not useful without describing its uncertainty. And there's several approaches to bring this out of reports and out of discussions into the model. One approach was to use different definitions for geotechnical units. That's something that I just showed. And here I want to also point you again to this DAUP guideline, where this topic or where this concept is explained in more detail. Then something that shall be included in the concept of IFC tunnel is a parameter distribution model. This is any kind of overlapping model that describes a certain property in 3D. May it be with a voxel model or with some shell models or with some other parametric descriptions. And this can be used to quantify. If you have an agreed classification for your uncertainty, you can, of course, provide this along with your model. Then you have the chance to use this geotech synthesis model, the model that connects your ground model actually to the design or to a certain alignment, to define uncertainties along these alignments with properties. And of course, in the factual data or in the recommended geotechnical parameters, you can work with property ranges to say the cohesion is, I don't know, 100 to 200 kilopascal. So that's something that is possible in IFC to use bounded values instead of fixed single values. Yes, one thing that is currently ongoing is more work on uncertainty p-sets to take existing ratings or existing approaches from literature, from scientific publications and so on, and include them as a property set to attach this to certain objects, like a contact, like a layer, but maybe also to the overall model boundary to say these and these and these are the uncertainties associated with this model. So the benefit would be that someone who receives this model gets all your input on the uncertainty along with the model. With this, I'm at the end, and I hope that there's some time left for questions.
Thank
Mickaël,
you,
where
Jonas.
are we? Yeah.
We have one question, but it's more about implementation. I mean, people say that in the tools software, they are only up to IFC 2.x-ray. So there was a question about the implementation of IFC 4.3 or even 4.4. So if you ask some info.
Yes, that always depends on the software vendors, of course, and this is the problem that we all face. We are working now, let's say, on the edge and pushing the limits and try to bring things into IFC candidate, but the classical BIM software or the most of the projects do not even use 4x3 because they are always behind, and there have been big jumps in the last upgrades. Of course, this will be a long way until this really reaches the market.
Yes.
I'm aware of this, and this is, of course, painful. But anyway, you have to start at some point. Yeah. And I don't know who's in this group, if somebody from software vendors, from the software developing side is here and can comment on this. But of course, this is a big hope for us. There's some viewers that even exclude the 4x4 candidates models, like BIM Vision, for example. You can open these test models that have been exchanged with the tech team. You can open them in BIM Vision, and there might be some others. But until this really reaches the geotechnical software that you can export your ground model from your modeling software, or that you can request test results or borehole logs associated with an IFC file, this is still a way to go.
Thank you. So, and there were also other questions, but the team answered them. Kazunori and Girl came to help. So I guess we
Great.
don't have more questions about that. So thank you, Jonas. And I will propose you a last presentation that is about OGC standards and also what we did in Geotech AI. So I will give the floor to myself to do that. And
Here you go.
let's go. Just let me know if you see my screen. Be helpful. Up.
Yes, you're there.
Thank you. So let's go back to this one. Hey, come on. Full screen, is it possible? Okay. My keyboard is dead. Okay, so to finish our overview about standards for geotech, here is an overview of OGC standards, especially one that has been mentioned before, that is GeoScience. So about the OGC, this is an acronym for Open Geospatial Consortium, home of geospatial innovation, collaboration, and standards. And this is a very large group that is about defining standards for different topics that have in common, especially the wish to expose the data in conformance with the FAIR principles. So make the data findable, accessible, interoperable, and reusable. So you may know that in OGC, there are multiple things that are addressed, but especially what you can find is some people from different domains providing data models in geoscience, for example, and also API, so application programming interface, or more exactly tools that enable to make the data accessible. So certainly OGC is well known for its APIs that make it famous. So some that you certainly have already used are the whole APIs, so WXS services, WMS, WFS, very convenient to access some data like maps and also geology data of any kind. And there are also a new series of APIs, so for example, API features and something API that I already mentioned. So regarding OGC and especially the data models for geoscience, so the main one is GeoSciML. It's a data model in order to cover geoscience as a general thing, starting with geology. Then there was a first extension for hydrogeology called groundwater ML2. And the way those standards are developed and extended are discussed in a group called the Geoscience Domain Working Group. So this group decide of the different extensions that should be made. And especially in order to do that, we explore possibilities with interoperability experiments. So we had one regarding the borehole. We also had a second one regarding environmental linked features about web semantics, and there was also the Geotech AI that I mentioned before. So all those activity aims to make the geoscience standards best as possible in order to address different purposes. So the interest from the OGC Geoscience domain working for Geotech, well, the first one, if I go back to the presentation of the paper from David Toll, was that Geoscience has been designed for that. So we first addressed the topic of geological maps and observation, but the idea of GeoSciML, and that's why it's not Geology ML, but GeoSciML for Geoscience ML, is to be able to extend it for other geoscience data, such as geotechnics. So the objectives we had when working on that topic were to have a semantic consistency in the geoscience community. So we do believe that the people of AGS, DIGS, and IFC that address geotechnics all belong to the geoscience community, and the idea was to avoid some barriers between us and to facilitate the exchange of data between us. So what we target was a seamless transition between GIS and BIM. You certainly use GIS daily, maybe also BIM, and the idea that these are two different environments, but still the data you may want to use are about the same thing, even if they are not represented the same way. So what OGC GeoScience Domain Group was bringing into that project was GeoSciML and Quantum ML2 as basis for extensions to other geotech. Our idea was also in OGC to show what other data models can do, including those in OGC. And the things that is pretty nice in the OGC standards is the connection with the OGC API or web services. So all those data models that are proposed by OGC have been designed in order to be made accessible from and with these APIs. So that's one quality the data models of OGC have. They go nice with some API. Regarding the deliverables we made from Geotech IE, so here is an example of what you will be able to see. For example, a concept we identify, the material sample, you can see the different flavor of it, depending if you are talking about IFC version, the OGC version, AGS and DIGS, and you can see the different definition and also the properties we identify that would be nice to have independently from the tools you want to use. So you have a lot of them. Material sample is only one of them, and all those descriptions are available on the wiki that is mentioned here. As I mentioned before, our idea was also to extend the standards from OGC. So as Jonas mentioned, GeoScience was a base for many things, groundwater ML2 also, but still there were things that were missing in order to properly address the topic of geotechnics. So for example, the geotech unit that has been identified as relevant for geotech purpose is proposed as a new concept in GeoSciML, and also we figure out to connect it to the existing objects we have in GeoSciML. Same for groundwater ML2, plenty of things that were already there but needed some extension. And also when it came to address the topic about the description of the surrounding constructions and also the design of the building, then there were also standards in OGC that can help, especially if you want to build this seamless transition between GIS and BIM. So if you don't have a model of your infrastructure or more exactly the surrounding construction in BIM, you may have them in GIS and it can be useful for your purpose. So we help you to find the suitable data for that. One of the other things we worked on is in this Geotech IE was how to provide the geotech investigation data. I mean, we have some long discussion in IFC if this topic should be addressed or not, and the idea was how to facilitate the reuse of the existing things, the existing data model like DIGS and AGS. So we work on the basis that is this ISO standard. So at first it was a OGC standard that came to ISO. That's something that happened, and we are happy for that. About how to describe these observations. So as you can see on the picture on the right, that comes from a colleague called Katishlai. There are multiple ways to say that the expression that phase is happy. So you can just mention it as a pair of parameter and value. But the idea in the observation measurement sample is to go beyond that and to provide the observation result and all of its context. So you will not just provide the results and what it is about, you will propose more information like the observed properties, the feature of interest, where the observation was made, who and how this observation was made. And this standards now also include the steps of sampling and preparation that we often use in geotechnics. So we work on this common basis, try to find the connection between AGS, digs, and also how it can be exposed on IFC in order to have this level of information to make the data reusable. There are plenty of other capacity, like the fact that you can link observation and you then have an idea of the provenance of the data. And this is something very useful in the purpose of geotechnics, to know how the data have been provided. So we work on that thing and extend that standard. And especially then we also extended an API called SensorSync API to fit the purpose of geotechnics. So this API comes very nicely with the observation, measurement, and sample data models that I mentioned before. And the idea was to extend it to a set borehole that are linear offensive data. So you can see how the data model is and which would say classes enable to describe what. So you have, for example, the description of your borehole, its location and trajectory. You can explain also the different samplings that have been made from it. You can associate observation to either a point or a line or also an interval in these boreholes or on the sample itself. So this was the data model we work on, and we tested it with AGS and digs, and Neil and Dan reported the results for that. So you can find them inside the wiki of our page, including a guidance, including a demo, and the plugin that has been developed are freely accessible to you. So as the kind of conclusion about OGC standards for geotech, I show you that the nice thing that we managed to identify the semantics we were using. It's not perfectly aligned, but we see differences between IFC tunnel, AGS, and digs. We made multiple proposals of OGC standards extension to target consistency in the geoscience domain. That's our main goal. And we also experiment one API that could help to provide geotech data. So the main use case we have in mind when doing that is that what is nice with the OGC standard is those API can enable to bridge the gaps to make the connection between BIM and GIS environment. So you can, for example, think about accessing geotech investigation from a BIM environment thanks to OGC API. You can think about also exposing data you already organized with AGS and digs thanks to OGC API. And also something we demonstrate was the possibility to access description of geotech objects in GIS from the BIM environment. So that's things we imagine would really help in order to target BIM and digital twin for geotechs. So here you go. That's hand from my side. And if you have any questions, I can answer them. But do we have some questions for me?
Let me have a look. No, it seems rather quiet on Slido.
Okay, I mean, it's no problem. We are already over 4 o'clock here in Paris. So I will just propose you to do the wrap up. And for this session, here you go. I share my screen again. Okay, so the wrap up, if my computer wants. Up, should be okay then. So the wrap up so I came back with my hat of vice chair of this group. Some conclusion and perspectives. So thanks to that topic, I think that we demonstrated that digital standards was not digital standard for geotech data is not a new topic. Some standards work on it since a long time and continue to do it. But digital twins and BIM relaunch the interest and also the need for geotech standards. It offers this possibility to work together. And of course, these targets offer new perspectives and also new technologies that could help to target what we dream of regarding the provision of geotech data. So there is another question about the role of ISSMGE TC222. So in our terms of reference, we plan to continue to support the activity of standardization that was started in Geotech IE, especially in connection with BSI, with OGC, AGS, and DIGS. And we also think that ISSMGE TC222 might be a place where we could discuss things that are more related to the domain of geotechnics, not necessarily about the technologies, but this could be a place where we could discuss about vocabularies that should be in common, like the list of the geotech procedures, the list of offsite properties, so we could have a common basis on that. I also opened the door to the APIs, as the DIGS and AGS mentioned that this is something in study for them. Regarding the next event, we will continue to offer you a nice workshop. We hope you love that one. The next one will be not too far. It should be, we will try to have it at the last week of May, between May 27 and May 31. It's not already scheduled, but we are working on that. The topics, we have two topics that we would like to address: National Geotech Database, or more exactly, countries that think that it's nice to share geotech data commonly to build sustainably. And also what we would like to explore is the links with AI, machine learning. So there is another TC in ISSMGE that is addressing that. So in order to help us to organize this, we would like to propose you to contact us and propose presentation. If you are happy to, we will be happy to receive that, and we will figure, based on the answer we will have, what we will plan. Another meeting, physical one, we should be in Lisbon at the end of August in order to have our first physical meeting of ISSMGE TC222. If you plan to go there, we will be happy to see you. Reminding you that you can follow us on our website, on LinkedIn, on YouTube. And if you want to become an ISSMGE TC222 member, then this is possible, but you have to get in touch first with your national society. So there is a list of the national society of ISSMGE that is available from that website. And if there are empty places, then you can candidate to become one of us, and we'll be happy to be with you. So thanks for your attention. I also would like to thank all the presenters that give their time in order to have these nice meetings. I hope you enjoy it, and I will say goodbye to you and see you soon. So thank you.